Hello Math 1224, this is Dr. P with Lesson Launch 15.1. The goal of this, I hope, short video is to introduce a couple of objects, algebraic objects you might see in sequence or series definitions that I want you to be able to quickly recognize some things about. The first of these is, well, let me give an example. Suppose I give you the sum from k equals 0 to infinity of, let's say, negative 1 to the k times k over 2 to the k. Alright, that would be kind of an example of what I'm talking about. So these things, k and 2 to the k, by now should be pretty familiar to you. But this might take some thinking about. What is negative 1 to the k? What does that mean? So I want to write out the first few terms of the series, because it's something you can calculate. You know how to calculate negative 1 to the k. It's just you may not have a ton of experience. But the reason I'm highlighting this, even though you could calculate this yourself, is because this is used a lot in series definitions to produce a very specific effect. So let's calculate the first few terms of this series. So when k is 0, I get negative 1 to the 0 times 0 over 2 to the 0. That's just going to be 0 because that k is 0 there. Now the next term is going to be negative 1 to the 1 times 1 over 2 to the 1. That negative 1 to the 1, that's negative 1. And then that k was 1. And then 2 to the 1 was just 2. And then the next term is going to be, let's see, negative 1 to the 2 is 1. It's a positive 1. K is 2. 2 to the 2 is 2. So I'm going to have 2 over 4. And I could simplify that to 1/2. But I'm actually going to leave that alone. And in fact, for that first term, I'm going to put an over 1 there, just to signify that the denominator there was 1, just so we can keep track of all that easily. All right, next term. So now I'm at k equals 3. I feel like video is kind of a weird way to do all of this, because I wish I could gesture a little bit more. But instead, I'll just put these values of k here. There we go. Okay, now when k is 3, the term I get is negative 1 to the third. Well, think negative 1 to the third, that's a negative times a negative times a negative. That's a negative. And then k is 3. And then 2 to the third is 8. And let's just do one more for good measure. When k is 4, I get, well, negative 1 to the fourth, that's a negative times a negative times a negative times a negative. And that's a positive 1. I promise I'll stop after this one. And then k is 4. And then 2 to the k, that's 2 to the fourth is 16. And this goes on forever, but that's the first few terms. Now you notice that what's happening with this thing here, this negative 1 to the k, is it's producing a pattern. The pattern of signs goes plus, minus, plus, minus, plus, minus, and so on. And that's what that's designed to do. Now suppose, on the other hand, you have some other series. Maybe you want to write this one in some notation. So let me just give this as an example here. I don't know, maybe you encounter something like this, and you'd like to find a way to express it. So I'm going to write 2 over 1, but let's see, I'm going to put that, and I'm going to leave that b for now. 2 over 1 minus 3 over 4 plus 4 over 9 minus 5 over 16 plus 6 over 25 minus 7 over 36, and so on. And I want to express this in some notation. Well, how would I do that? So first of all, I can just try to account for all of the things that are easily accounted for here. For example, you might have noticed by now that the denominators of these fractions, they're all perfect squares, and they're consecutive perfect squares. So I think that the first thing I'm going to write down here, I'm going to write some kind of sum notation, because I know I'm adding a bunch of things up, even though some of the things are negative. And I'm going to include in here, let's see, I think I'm going to want n to start at 1. I could use n or k, it doesn't matter. And I think that if the first term has a 1 squared in the denominator, the second term has a 2 squared, third term has a 3 squared, I probably want the nth term to have an n squared in the denominator. That seems to be a sound approach there. And then what about the numerator? Well, the numerator goes 2, 3, 4, 5, and so on. And you'll notice that when I have, for example, a 4 squared in the denominator, I've got a 5 up top. And when I've got a 5 squared in the denominator, I've got a 6 up top. So this is the fifth term, and yet my numerator is 6. And in the sixth term, my numerator has a 7 in it. And I'm never minding the signs for right now. We'll figure that out later. But it looks like the numerator is n plus 1. Okay, and that would be almost good enough, except, well, wait a minute. If I add all of these up, and I let this go on to infinity, I'm going to have a bunch of positive terms, and it should be the case that half my terms are negative. This one's positive, this one's negative, this one's positive, this one's negative. So what if I try to produce the same effect by sticking in there? So I'm going to multiply that whole thing times a negative 1 to the n. Would that work? Well, if I try testing a few terms, if I try testing the n equals 1 term, for example, that's going to be n equals 1, so I get 2 here, and then negative 1 to the 1 here, and then 1 here. So that negative 1 to the 1, that's going to produce a negative sign, and I actually want this to have a positive sign. And then when I try n equals 2, I get 3, and then negative 1 squared, that's positive, over 2 squared, that's 4. So I get a positive term here where I wanted a negative here. So this is producing, if n is starting at 1 here, you'll notice in the previous example, k was starting at 0, but if n starts at 1, then this thing here, this widget, produces the pattern minus, plus, minus, plus, minus, plus. And I want it to produce plus, minus, plus, minus, plus, minus. So one way of fixing that is to just take each term and flip it. I mean, I could actually literally just do this. Stick a negative sign on there. But it might be more elegant. Let me see if I can erase all of that. Yeah, there we go. It might be more elegant to do the whole thing this way. If I'm going to multiply by a negative sign, that's like multiplying by another negative 1. And I could just consolidate that with negative 1 to the n. That would produce this. Sum from n equals 1 to infinity of negative 1 to the n plus 1. I always like putting that out front if I can. Times n plus 1 over n squared. And I think you can check for yourself that that would produce exactly the series that we want here. Now, of course, this all assumes that these series terms go on and on and on, according to the pattern that we've sort of gleaned from the data here. And you always have to assume that with these, or have someone tell you that that's what's going to happen. In this case, I'm assuming that the pattern continues to be that the numerator increases by 1, the denominators are consecutive perfect squares, and the signs go plus, minus, plus, minus, plus, minus. Anyway, that is how we express one of these in sigma notation, including that negative 1 to the n plus 1 bit. All right, one more thing, and then I promise that'll be the end of this video. We'll move on to doing some mathematics problems here. I don't know, that was kind of a mathematics problem there. I feel like finding a pattern and expressing it, that's a pretty good math problem there. Anyway, now I want to talk about some very exciting numbers. Very exciting because they have exclamation marks at the end. Now, you've probably encountered this at least once before. This is called a factorial. And it's pronounced in factorial. It's not pronounced in. It's pronounced in factorial. So the way that this works is if n is a positive integer, remember that's an n with a double back on it. If n's a natural number, then we define n factorial to be the product of all natural numbers less than or equal to n. So that's equal to n times n minus 1 times n minus 2, and so on down to 3, 2, 1. And of course, even by writing this, I'm sort of assuming that n is bigger than 3, right? Because all these terms wouldn't be there if n were something like 2. So you kind of have to use your imagination when I'm writing a representation like this. Anyway, sometimes it is useful to be able to write n factorial in that way, because sometimes I'm going to encounter something like, now I'm getting a little bit ahead of myself here, because there's one part of the definition missing, but I can't resist the opportunity to do this. Actually, let me do this. I'm going to write n plus 2 factorial. Now, by the way, if you mean the factorial of n plus 2, you need to put the n plus 2 in parentheses. If I write this, it just means n plus 2, no, n plus the factorial of 2, and that's not what you mean here. So I'm going to write n plus 2 quantity factorial over n minus 1 quantity factorial, and see if I can simplify this, because we're going to encounter problems like this quite often. So that factorial on top is the product of all the natural numbers from n plus 2 down to 1. So if I sort of imagine myself starting at n plus 2 and counting down, I get n plus 2, and then n plus 1, and then n plus 0, and then n minus 1, n minus 2, and so on down to 1. And then if I imagine dividing all that by n minus 1 factorial, well, what do I get if I start at n minus 1 and count down? I get n minus 1 times n minus 2 times etc. down to 2 times 1. And you'll notice that when that happens, I end up dividing this factor by this factor by this factor, all of these factors by all these factors, the 2 by the 2, the 1 by the 1, and I'm left with just, God, this yellow color is kind of ugly in my opinion. Sorry about that. It's not pleasing at all. And that becomes, that's equivalent to, let's see, what is n plus 2 times n plus 1? That's like n squared plus 3n plus 2, I think. So that's n cubed plus 3n squared plus 2n. Anyway, all that is just to illustrate that if you see an expression like this, it looks kind of nasty, but actually may simplify to something rather nice. I mean, that's a polynomial. Hard to get a lot nicer than that. So just something to know. Now, one more thing, very important thing about the definition that I left out at the start. So n factorial is defined only for natural numbers and for 0. But I didn't tell you what 0 factorial was. We define 0 factorial to equal 1. Now that's, so I'm just stating that's the definition there. And if I say we're going to define it this way, you don't have a lot of standing to argue with me. But a lot of people always wonder, why in the world does that make sense? So they think about this and they're like, why is that even a logical thing to do? I don't know why my faces have noses all of a sudden. That doesn't make sense. But anyway, a lot of people think, well, 0 factorial, if you're multiplying by anything including 0, that's just 0. Shouldn't 0 factorial be 0? Well, let me say a bit about why this would make sense. So I actually want to give my favorite explanation of this, not the most algebraic one. But when we think about n factorial, this counts the number of ways to put n things in order. For example, if I consider the letters A, B, C, then how many ways are there to put those 3 letters in some order? Well, I have to pick a sequence of 3 letters where the 3 letters come from A, B, C, and I've got 3 choices of what I'll put here, A, B, or C, and then once I've picked that, I'll have 2 choices of what to put here because there's 2 letters remaining, and then once I've picked that second letter, there's only 1 choice of what to put here. So like, for example, if I choose to put B here, then I can only put A or C in this second spot. So suppose I choose A, and then once I've chosen that, then there's only 1 choice for what goes here. And you can actually count out that there are 6 ways of putting those 3 letters in order. I'm just sort of demonstrating this. This is probably gratuitous at this point, but those are the 6. And that's equal to 3 factorial, 3 times 2 times 1. Well, how many ways are there to put 0 things in order? That would tell us what 0 factorial would be. Well, if I have nothing, and I want to put nothing in order, then, well, I'm done. I did it. There was only one way to do it. There's only one way to do nothing in mathematics, and that is to do absolutely nothing. So that's one reason why 0 factorial is 1. And the more algebraic argument, by the way, if you're sick of watching this, you can stop now. If you're willing to accept that 0 factorial it just is 1, then you don't have to watch all the rest of this. But you might find this next part a little bit more, I don't know, intuitive, because this one you kind of have to believe that n factorial is supposed to do this combinatorics work for us in order for that argument to be persuasive, that 0 factorial is 1. But here's the other one. You'll remember earlier I said that one thing that we know is that we can often do a lot of cancellation in expressions like these. And in fact, this is equal to, well, what would this be equal to normally? This would be n times n minus 1 times n minus 2, etc., down to 2 times 1. And then this other thing, this denominator is n minus 1 times n minus 2 on down to 2 times 1. So if we do all the mass cancellation that occurs here, I know that some teachers don't like to say cancellation. They'll say something else instead. How do I create new colors here? There we go. It's like I've forgotten everything about explain everything. So I end up dividing these out. Divide out all these factors. Well, remember there's factors in there, and the dots, they're just hidden by the dots. That's all equal to n. Okay? So if we believe that as a general principle that should be true about factorials, that and actually sometimes people use this as the, oops, whoa, didn't mean to give you all vertigo there. If some people define the factorial this way, they define that n factorial should by definition equal n times n minus 1 factorial. So this is like a recursive definition of n factorial here, is that they start with 0 factorial being 1, and then they take this recursive definition here. Well, if we want this to work when n is 1, then we need 1 factorial to equal 1 times 0 factorial. And if that's going to be true, and we want 1 factorial to equal 1, then that means this has to equal 1. There's no other option. It certainly can't be 0. If it's 0, then 1 factorial is going to wind up being 0, and all the other factorials are going to wind up being 0. We would not want that. So anyway, that's another reason why it's just good practice to define 0 factorial to equal 1. And the bad news is, whether you like it or not, you're going to have to believe that, because everything that we do with Taylor series in the next chapter is going to depend upon that. So anyway, so I gave you 2 explanations, and if you don't like those, then I'm just going to assert my mathematical authority here and force you to believe what I want you to believe, which makes this pretty much like all the other classes you take at UTSA, I suppose. Anyway, so the purpose of all that was to talk about these 2 fun little objects, -1 to the n and n factorial. As I say all this, I recognize that came out to 17 minutes, so I totally failed my mission of making this video short, but I'm hoping that that'll help with the next few videos, which will have to do with determining whether series are convergent or divergent, so stay tuned.